Hello, my name is Bruce Archambeault, and today I'm going to talk about one of my favorite topics, the ground myth. We think about ground as this perfect thing. You can never have too much ground. I hear people say, just ground it, and it'll be okay. Well, ground could be many different things, and we need to be more descriptive. Really, we don't have the ground that we do have is the dirt, and that's a reference for the lightning and for AC power and all kinds of things, and that's fine. That needs to be there. But in a circuit board, we don't have any dirt. We try not to have dirt. And so we're really talking about a ground return plane. Actually, we're talking about a return plane and not a ground return plane. But I use the word ground return because at least people kind of think they know what ground is, and so they can then when I say return, they say, oh yeah, that's what he means. Well, one of my favorite phrases is ground is a place for potatoes and carrots. The idea of using earth or reference is actually more relative and more accurate. I think that we'll talk about the original use of ground, but the bottom line is the inductance associated with the connection to the ground, whatever that ground is, that inductance is going to depend or make the ground connection not as well as it should. So when we're talking about ground, we really mean safety ground or power ground or signal return or power return or chassis shield or earth, shield earth. All those things are possible what we're talking about. So we need to be more specific. And the other thing to remember is that ground is not a current sink. It's not like I'm going to put all my electrons into this thing called clean ground and then I can pass my EMC requirements or whatever. I think that we need to make sure that the current gets back to its source. Current will always get back to its source, but in this day and age of looking at just voltages on signal integrity analysis, then we forget that there's current, and the current has to get back to its source. And that's the bottom line. So where is ground? Well, it's at zero potential, and that happens at infinity. And so if you want to ground something, you need a really long wire if you want to go to zero potential. Now, we think about a metal plate. Like I've got an example here of a steel metal plate about a foot by a foot. And at 100 kilohertz, it's only 4 milliohms across that steel plate. But at gigahertz, it's almost half an ohm. And if we want to connect a via, like from a capacitor, to our ground return, then this is the impedances that you see. And you can see up at a gigahertz or 2 gigahertz, we're really getting some large numbers associated with that, just a simple via. Now, people talk about the single point ground, and that's really a myth, because at low frequencies, you can have single point ground. Absolutely. This is very low frequency. You get up into the megahertz and so forth, and the current is going to find its way back to its source. That could be through parasitic capacitance, through parasitic inductance, or however it might get there. And so it will get back to its source. If we want it to go through the air, through the capacitance and inductance associated with the just the electromagnetic connection, then we're going to be in big trouble when it gets to the EMC lab. We need to make sure that we have ground properly. So here's an example of two boards, and I put the capacitance between the ground planes, the ground reference planes on there, just to show that there's more than one path. Even though my intentional signal path was through the flex cable, I had all different kinds of capacitances that were, and I'm not showing inductances just because it's so much to show. So where did the term ground originate? Well, I think it originated either with teletype, or telegraph, I should say, in the old Western days. Remember that the cowboys would go out to the telephone pole and cut the wire. Now, if they were Clint Eastwood, they'd just shoot the wire. If they were Arnie Schwarzenegger, they'd probably blow up the pole, and everybody else climbs the pole to cut the wire. But the point is, there's only one wire. Well, wait a minute. Current has to go out and has to come back. So how's it come back? Well, they discovered that having two wires, one going out and one returning, was expensive. It cost 2 times the cost of having one wire. And so what they did is they stuck the second wire from the two receivers into the dirt. And the dirt returned the current. But, you know, how fast can you do this, right? Maybe somebody that's really good can do 10 words a minute, but that's pretty slow technology. And so having the ground return current going through the dirt worked just fine. The other possibility is lightning strikes. Now, here in the U.S., we have a lot of lightning strikes, especially bad storms out in the Midwest. And if the lightning strikes, then the barn burns down, and that's a bad thing. And so we want to do something. And so if we put a big rod on here, lightning rod, and then the current actually goes to the ultimate reference, which is the dirt. So that's how ground came from. Now, you've all heard about the Human Genome Project. They found a gene that makes us think that ground is good. I actually had somebody ask me for the reference for that once, and I had to tell them I was joking. But you would think it's in our DNA to have a ground is good gene. So again, when we say ground, we're talking about different things. Here's an example of some ground symbols. I like the floating ground because I'm a sailor and I like floating ground. We can have earth ground there, and the one I really like is grounds for divorce. And I suggest that you use these symbols in your schematics because at least you'll know not to take ground seriously. I don't know that anybody has ever taken me up on that suggestion, but I'm hopeful for one day. So the bottom line is current will always flow in the path of least impedance. You know, we talk about the path of least resistance, and that's true at DC. But at low frequencies in DC, that's not where we're working and where we're worried. So we're worried about the path of least impedance because the impedance includes the inductance. And really it comes down to, it's not the resistance so much as it is the inductance to make sure that the signals get back to where they're going. So here's an example. I want to get to the next example here. So here's an example of a schematic, and we have this wonderful ground term on here. Yes, it's there. The lighting in here is such that I couldn't see it. But the schematic is dimensionless. Now we have to actually put the capacitors somewheres and put the traces somewheres, and the return current is going to take the longer path back just because it's a shorter, least amount of inductance. So at low frequencies, it takes the path of least resistance. At high frequencies, the return current would take the path of least inductance. And if you calculate the loop area under a trace, you know, you've got maybe 10 mils of separation between the reference plane and the trace, maybe 5 mils, I don't know. It all depends on this technology. But the point is that that dimension underneath there, if you calculate the loop area of that versus the loop area of going straight across, you'll see that the inductance is much lower for the path of least impedance. So I created this U-shaped channel here, and basically I've got a source on one end and a load at the other end. It's just shorting out. I've got a ground return plane on there and a trace, and I'm going to drive a current, and I want to see how the return current goes. So at low frequencies, the current will come out on the trace. It has to, I'm forcing it to, but then the return current will be in the ground reference plane, and it'll just come through straight across. That's for low frequency. At high frequencies, you can see the path is different. So here above, we got a 1 kilohertz, and you can see that all the return current in the red is going straight from the load to the source. But at high frequencies, a megahertz, which is not really that high by today's standards, all the return current is in the reference plane, in the ground return plane. And so it's taken a longer path, but it's a path of least inductance. And here is another simulation that I used where I just found the inductance of that trace. And at low frequencies, the inductance was high, and at high frequencies, the inductance was low. And that supports what we saw before. So I'm fond of saying that there's no such thing as voltage. A friend of mine told me that once years ago, and I was shocked because I had a voltmeter. And but what he meant was, if you look at Maxwell's equations, there's current, there's electric field, and there's magnetic field, but there's no voltage. So as a fundamental quantity in the universe, voltage is a man-made thing. And in fact, this is the formula to create voltage. It takes an electric field over some distance, and it integrates that, adds it all up. Really, integration is just a sum of all the parts, and then the voltage comes from the electric field over this distance. So current is what really we care about, and this is a formula to show the current radiation, the electric field radiation, I should say, and everything in the parentheses is a constant. Omega is frequency, c is the speed of light, and that's a constant. R is the distance to our observation point. And so outside the parentheses, we have the sine of theta. That's just the angle between the current and our observation. And then the denominator is a constant. We have current and length there, and you see that with all the different variables there, the thing that's really creating an electric field is the current. That's the important point. So if we have a light bulb and a battery, we'll turn on the light bulb if the battery is working properly and the connectors it's all connected. If we disconnect the battery, the current stops going. Well, duh, of course. The real thing about current is that there's a pulse of current that goes down the signal line. Now, many of our signal lines are larger than a pulse width on the signal line, and that is going to mean that the current goes down the trace, and it doesn't go all the way to the end and then return in the return plane. It has to return with a path of least inductance. And so it's going to basically be showing, it's similar to a tank treads. The tank goes forward, and immediately underneath it, of the tank treads, is the return. And that's basically what happens as we go down a circuit board. The return current, we get a pulse of current, and you can see that there's current on the trace, there's current on the ground reference plane, and there's some capacitive current in between the two, causing that to be a loop. And so we get a loop there, and that's how the signal goes down the trace. Now we might have a microstrip where the traces on the outside. We might have a strip line where the data line is in between two ground reference planes, or we might have some many layer stack up. The bottom line is the return current for this top signal here is not going to return on this plane down here. If I call that ground, for example, it's going to return on the top of this nearest plane, regardless of what I call it. If I call it apples or pizza or just ground return, it's going to return there. So here you can see a microstrip, and what I'm doing is I'm driving the microstrip relative to the VCC in this case, and you can see the blue lines that all terminate at the VCC there, and wherever the blue lines terminate, we get current, and most of the current is directly underneath the microstrip. Some of the current stretches out a little bit and tries to reduce the path of least inductance there, but the major part of the return current is going to be underneath the trace. If I have a differential mode, then I still have the electric field lines terminating on the VCC plane, and there's a few lines that go between the two traces. Only a few lines. This is very weakly coupled. It's mostly coupled to the reference plane or the ground return plane, because you can see there's more lines going down to the nearest plane than there is lines going between the two traces. We can do the same thing for a strip line. This is a symmetrical strip line. I happen to label ground and VCC for the two planes. And you can see that the field lines terminate on both planes equally. So the current will be the same they will be the same equally on both planes, regardless of what we call them. And the same sort of thing happens for differential strip line. And asymmetrical strip line, with the traces closer to one plane than the other, you can see that most of the lines of fields are terminating on the VCC, and some are terminating at the further plane, which I labeled ground return here. Okay, and the same thing for differential. So the idea of grounding is very misleading. I think that the number one cause of EMC problems is the misunderstanding that people have of ground. And I've spoken to many professors, and there's only a few schools that talk about this ground thing without it being this magical, wonderful thing that all gets connected with zero inductance between it. The return current is the key. Think about where the return current is going. The outward current obviously goes on the trace. The return current is going to come back underneath the trace, as I showed you, as long as you don't interrupt that path. If you have splits because you are running against a power layer and you have different power islands, that split is going to cause extra EMC problems. And so you want to run those high-speed traces relative to a plane that's not broken up at all. So again, high frequency versus low frequency. The low frequency, it's a path of least resistance, but for EMC applications, we're up in the higher frequencies, and so we have to worry about inductance. Inductance is everything. And remember, ground is a place for potatoes and carrots. And if only I had a shovel here, I could dig up a couple for you. I hope this has been helpful, and thank you for listening.